Hello, welcome to this talk on Penrose Inequality in interdiscrete space. This talk is based on work done with Husain at UNB. The main idea behind the work is to look at whether a singularity that forms as a result of gravitational collapse is it shrouded by an event horizon or not. These results have been mathematical curiosities till now. However, recently, with the result coming from Event Horizon Telescope, we've seen that they've achieved the ideas in general relativity relating to black holes, particularly, have sort of received a new reality. And so that's the purpose of this talk as well, to sort of uh, bring out what we have been doing in the case of black holes and event horizons, and what does it all mean in light of the results or in light of the picture of the black hole which we've recently seen. So I've put on this title slide. The object here is the M87 galaxy, which is a radio galaxy 53 million light years away from Earth. The galaxy is, uh, it shows that there is a jet which is emanating from that galaxy. The jet itself is 5,000 light years away from that galaxy. The galaxy hosts a supermassive black hole from which this jet is originating. And recently, the Event Horizon Telescope announced that they have taken a picture of uh, the supermassive black hole that's residing within that galaxy. And this is what it looks like. Although it seems a bit fuzzy here, but keep in mind that this telescope is looking at this particular object with a really high magnification. The magnification can be stated in the following way. Suppose you have a quarter in Los Angeles, then you can read the date on that quarter in Los Angeles from New York. That's the kind of magnification which we have here. So for a first image, even though it's slightly fuzzy, it's still a big technological advancement and a technological feat. However, let's see what the image shows. First thing is that it looks like kind of like a donut. So we do see an interior region which is of diminishing brightness from the exterior. That region is, in a sense, the black hole or the supermassive black hole that's residing in that galaxy. Of course, the yellow circle which I've drawn here, it's not really the event horizon of that black hole, but it's what is called the photon capture surface. It's the last interior surface where light can have a stable orbit before getting captured. So that's the event horizon, sort of like indication of existence of an event horizon. So just to lay down some facts, so this is M87 in the Virgo galaxy cluster. The black hole, central black hole, is 6.5 billion solar masses. It accretes 90 Earth mass per day, and it's shifted from the galactic center by around 25 light years. And the angular radius of this particular region, or the black hole shadow, is 20 microarcsecond. So how is this important with respect to our own research? Uh, there is a statement in general relativity referred to as the weak cosmic censorship hypothesis. It's a statement that a space-time singularity arising from gravitational collapse of reasonable matter must be shrouded by an event horizon. The statement was given by Roger Penrose in 1969. Penrose also proposed an initial data test for the weak cosmic censorship hypothesis in terms of a Penrose inequality. What is this inequality? Consider spacetime that is asymptotically flat and also a solution of general relativity with matter satisfying dominant energy condition. That is, there should not be any superluminal effects. Now, if a Cauchy slice sigma of this spacetime has some ADM data, which is given by a 3 metric of that slice, its conjugate momenta pi AB, and the matter variables, the density and current rho and j. Now, suppose there is an outer trapped two-surface S of area AS on the slice, and if M is the ADM mass of the data on the slice, then the conjectured inequality is that area of this slice, area of this surface S, is always less than equal to 16 pi m squared. Or if we use the mass area relationship, what this means is that the mass contained in the apparent horizon, which is the boundary of this trapped surface, mass contained in the inside the apparent horizon is less than equal to capital M, the total mass. So that means during a collapse, a quasi-local mass cannot exceed the total mass of the data. This fits with intuition, since for an ongoing gravitational collapse, the region between the apparent horizon and spatial infinity will contain uncollapsed matter, the matter which still has not gone inside the black hole. The proof or disproof of this inequality is an important problem in relation with gravitational collapse. It's also a challenging problem in mathematical relativity, and it has received continuous attention since its formulation by Penrose in the early 70s. So how to test whether this inequality holds or not, if we are to do some theoretical tests on it. So the procedure is laid out. Step 1, one gets the data that solves Hamiltonian and diffeomorphism constraints. To do that, you choose a 3 metric or slicing, solve for the conjugate momenta by specifying matter distribution that respect dominant energy condition and asymptotic behavior, such as the mass function should asymptote to the area mass. Step 2 is compute the null expansions from this data and find the locus of apparent horizon. Find the location of apparent horizon where both expansions vanish. That's the definition of a trapped surface. We want to know where that trapped surface is in order to find the mass within that trapped surface or mass within the apparent horizon. So as finally step 3, we check the mass contained in the apparent horizon with the total mass, and thus find whether that inequality holds or is violated for that particular data. At present, this inequality for asymptotically flat case has been proven for arbitrary time symmetric data and in many special cases. However, we have had recent theoretical numerical reports saying that there might be a violation of the weak cosmic censorship conjecture in four-dimensional antidigital space. So the authors have done some numerical work in which they follow curvature as the gravitational collapse proceeds and notice that this curvature blows up or it diverges at the apparent horizon. So somehow finding out or sort of meaning that there has been some sort of violation of cosmic censorship, that there is a singular behavior not far from apparent horizon. However, the authors do not touch the Penrose inequality, which is the ultimate test of cosmic censorship. For if we see the words of famous relativist Bob Wold mentions, failure of this inequality to hold in any example would be nearly fatal to cosmic censorship, as only a few small loopholes would remain, such as the possible unsuitability of matter, the possible non-generic nature of the example, and the very remote possibility that the black hole does not become asymptotically stationary. So in this sense, Penrose inequality is sort of like an ultimate test for testing whether there is a violation of cosmic censorship or not. So therefore, it's useful to formulate and study generalization of Penrose inequality to asymptotically ADS case. This requires a specification of asymptotic ADS data satisfying GR constraints, which are given as below. So you see here there's a fact. So the first one is the Hamiltonian constraint, and the second equation is the Diffie constraint. You see the factor minus 6 by L squared in the Hamiltonian constraint. That is precisely a negative cosmological constant, since ADS space is space of constant negative curvature. So that comes from a negative cosmological constant. Now, ADS fall-off conditions have been studied before by, for instance, Heno and Tettelbaum. These are modeled by a Schwarzschild form of ADS black hole. However, we use a different form for the asymptotic ADS black hole, which is written in the following manner, such that T equal to constant surfaces are spatial slices of constant negative curvature. This is called the Painleaf-Gulston form. So we need to, before we formulate the inequality, we first need to calibrate our definition of quasi-local mass, because the usual definition which is given is valid only for asymptotic flat case. So we need to modify that mass definition. So Hawking defines mass contained in any surface is related to the area of that surface times in integral over the null expansions of that surface. So this definition, if we use it for this metric which we have for ADS, and we take these surfaces to be spherical surfaces on T equal to constant slices, then what we see is that the mass turns out to be divergent in the limit r goes to infinity. So as we are increasing r, we should have recovered capital M instead of any divergence. So there's this extra factor coming up. Therefore, we use a regulated definition for the Hawking mass, in which this limit of r going to infinity is fixed, so that mass then is given by capital M, which it should be the total mass of the data on the slice. So using this definition of mass, which works for ADS, we can now formulate our Penrose inequality, and the statement of the theorem is the Penrose inequality, which is mass using that definition contained inside the apparent horizon, is always less than or equal to capital M, the total mass. And this inequality holds for general spherical symmetric asymptotically ADS data of the form given by the following equations, where the 3 metric is just spatial slices of constant negative curvature, and momenta is non-zero, in the sense this is a time asymmetric data. For time symmetric data, pi AB is 0. So where f and g are arbitrary functions that need to have ADS fall off, and that happens if matter distribution satisfies the dominant energy condition. Now, since any spherically symmetric asymptotic ADS metric can be put into constant negative spatial curvature form, this result holds for all spherically symmetric asymptotic antidesitter spacetimes. So I'm not gonna prove the inequality in this talk, but I'll just give you the idea how to prove it. So one thing to notice, again, I will highlight that this proof of Penrose inequality in asymptotic ADS is only for spherically symmetric case. So this is how one sort of proves it, the idea of the proof. We are essentially obtaining mass functions, and we want to find want to sort of see that or prove that mass contained in the apparent horizon always less than some total mass in the data. So that's the total mass. Now the mass functions could be of various forms. There could be something like this red curve, or a mass function would be something like the blue curve. The main point is that they should asymptote to the total mass. Now, the next thing is step 2 and 3, finding out where the apparent horizon is. So one finds the apparent horizon by looking at where it intersects the mass function. The location of apparent horizon is given by that, and if this intersection is below capital M, then the inequality holds. However, if it lies above capital M, the inequality is violated. So red is the violating type of mass function, whereas blue is the obeying mass function. By looking at the tangent to these curves or the derivative of these mass functions, one can and noting that it should asymptote to capital M and matter should satisfy dominant energy condition, one can show that red type mass functions cannot occur, or mass must asymptote to capital M from below. That's the important point. The red type mass functions cannot occur. That essentially proves the inequality. The case of axisymmetric asymptotic ADS is still open. What I'll emphasize again, we've proved that a gravitational collapse in asymptotic anti-de Sitter space that's of spherical symmetric will always have an event horizon. The Penrose inequality holds, cosmic censorship is valid, so there will be an existence of event horizon in such cases. The example which I mentioned, the report which I mentioned earlier of guys who are saying a violation that involves axisymmetry, and proving the inequality for axisymmetry is slightly more difficult and challenging and is left out for the future. So I'll stop here. Thank you.